Hello friends. So in today's session, which is the concluding sessions of fundamentals of trigonometric functions, uh, part 1 and 2 which we have discussed so far. So I'm assuming that before you go through this session, you have gone through this part 1 and part 2 in the YouTube which I've discussed, because this part 3 concluding session is in the continuation of the previous two, and this is the last session. And then in this session itself, I will be discussing some of the complex examples using the identities which have been discussed in 1, 2, and also in these sessions. So let's start with today's session, uh, which was remaining till now, and we'll be covering it. So till now we have covered sin x plus y, cos x plus or minus y, cos x plus or minus y in the previous sessions. So now let's go through the other identities and the proof of that. So let's start with the first one, which is tan of x plus y, which is equal to sine of x plus y plus cos of x plus y, which we can further write it like sine a cos b plus cos x sine y, and then in the bottom we can write cos x cos y minus sine x sine y, right? Okay, now we divide the numerator and denominator by cos x and cos y, so this will become sine x cos y divided by cos x cos y plus cos x cos y divided by cos x cos y, and then here also cos x cos y minus sin x sin y divided by cos x cos y. So cos y, this one becomes tan x sorry, this was sin y, I'm sorry. So this becomes tan x plus tan y, and in the bottom it becomes, this is 1 minus tan x tan y. So basically tan of x plus y is equal to tan x plus tan y 1 minus tan x, right? In the similar fashion, we can derive tan of x minus y. What we need to do, we just replace this one with minus y, and we will get tan of minus y. We know it is minus tan y. Well, suppose we write it like that, tan of minus y, and then 1 minus tan x tan of minus y. So tan of minus y is minus tan y, and then it becomes 1 plus tan x tan y. Similarly, we can derive the other identities, which is cot of x plus y, and in the similar fashion we can prove it. Cot x cot y minus 1 divided by cot x plus cot y, and then cot of x minus y is equal to cot x cot y plus 1 divided by cot x minus cot y. Okay, now other identities are cos of 2x. Cos of 2x is nothing but cos of x plus x, which is cos a cos b minus sin a sin b, which is equal to cos square x minus sin square x, which is again equal to cos square x minus 1 minus cos square x, which gives 2 cos square x minus 1, or we can write this one as also 1 minus sin square x minus sin square x is equal to 1 minus 2 sin square x. So we have 1, 2 and 3. So this is cos 2x formula we can write. Similarly, we have sin 2x, which is equal to sine of x plus x, which is sine of a cos of a plus cos of a plus sine of a, which is nothing but 2 sin x plus x. Okay. Now, similarly, we can also write we can extend this further is equal to 2 sin x plus cos x divided by sin square x plus cos square x, because this is 1, and then if we divide both the sides, dividing each term by cos square x, so like this one becomes 2 sin x cos x divided by cos square x divided by sin square x by cos square x plus cos square x by cos square x. This further becomes 2 sin x by cos x, and this becomes tan square x plus 1. So it is 2 tan x divided by tan square x plus 1. So what we proved just now is sin 2x is 2 sin x cos x, which is also equal to 2 tan x divided by tan square x plus 1. So you can use any one of them depending on what kind of question problem we need to solve. Continuing further, we will be doing tan of 2x. Now tan of 2x is equal to tan of x plus x, which is tan a plus tan b 1 minus tan a tan b. So 2 tan x divided by 1 minus 2 tan square x. Okay. Then we have sine of 3x. Now sine of 3x, we can write it at sine of 2x plus x, which is we have sine of 2x cos of x plus cos of 2x plus sine of x. Now sine of 2x is 2 sin x cos x, and then we have cos x, and then cos of 2x we have 1 minus 2 sin square x, and then we have sin x. Okay, so then if we take the 2 sin x as common, you know, uh, this will become, so this will become 2 sin x cos square x plus 2 sin x into 1 minus oh sorry, and then it becomes, so it is 2 sin x cos square x plus sin x minus 2 sin cube x. And if we open this further, 1 minus sin square x plus sin x minus 2 sin cube x. So this becomes 2 sin x minus 2 sin cube x plus sin x minus 2 sin cube x. So it becomes 3 sin x minus 4 sin cube x. So this is of sine of 3x. In the similar fashion, we can also derive cos of 3x, which is cos of 2x plus x, which finally, if we go the same steps as we have gone previously for sine 3x, we can prove it 4 cos cube x minus 3 cos x. And continuing further, let's derive tan of 3x is equal to tan of 2x plus x, which is equal to tan a tan b divided by 1 minus tan 2x tan x. Now divide, you open this one also, tan 2x, so that becomes, this becomes 2 tan x divided by 1 minus tan square x plus tan x, 1 minus 2 tan x, 1 minus tan square x into tan x, right? Now, so this top one becomes 2 tan x plus tan x minus tan qx. Bottom one becomes 1 minus tan square x minus 2 tan square x. So this, if we simplify further, it becomes 3 tan x minus so this become 3 tan x minus tan cube x divided by 1 minus 3 tan square x. So basically, what we proved just now, tan of 3x is equal to 3 tan x minus tan cube x divided by 1 minus 3 tan square x. This covers up to this, and then further other identities are, we have cos of x plus cos of y. Now cos of x plus cos of y, and then sine of x plus sine of y. We need to derive this. So how to derive this? So let's do cos of x plus y. We know cos a cos b minus sine a sine b, and then we know cos of x minus y is equal to cos x cos y plus sin x sin y. Okay. Now if we add this, cos of x plus y plus cos of x minus y, we get 2 cos x cos y. So if we add this, this gives this. Now let's x plus y is equal to theta and x minus y is equal to alpha. So it becomes cos theta plus cos of alpha is equal to 2 cos of theta. I'm sorry. This becomes like this. So if we say x plus y is equal to theta and xy is equal to alpha, then x is equal to, so x is equal to theta plus alpha divided by 2 and y is equal to theta minus alpha divided by 2. So if we replace this over here, it becomes cos theta cos alpha is equal to 2 cos of theta plus alpha cos of theta minus alpha. So this is the formula. So if we replace theta with x and alpha with y, it becomes cos x plus cos y is equal to 2 cos of x plus y divided by 2 x minus y. Basically, the reason we replace with theta and alpha, because theta and alpha are real values, so it can take any values. You can put a, b, c, so cos a, cos b. So we put it back over here, so it will have the same value. So the identity which we proved just now, cos x plus cos y is equal to, we got it, 2 cos of x plus y divided by 2 sine of x minus y divided by 2. So in a similar fashion, we can also prove sine x plus sine y, which will be equal to 2 sine of x plus y divided by 2 and cos of x minus y, and then cos x minus cos y is equal to 2 minus 2 sine of x plus y divided by 2 sine of x minus y divided by 2, and sine x minus sine y is equal to 2 cos of x plus y divided by 2 sine of x minus y divided by 2. So these are the identities we will be using in the trigonometric functions, and then finally, using the same identities which we discussed just now, we can also derive these additional identities. 2 cos of x cos of y is equal to cos of x plus y, cos of x minus y. You just put the values over there. So in place of x, you put x plus y, and so in case of cos a plus cos, we just proved it. So if you put in place of x plus y, you will get this. And similarly, we can also prove 2 sine of x sine of y is equal to cos of x plus y minus cos of x minus y. And then 2 sine x cos y is equal to sine of x plus y plus sine of x minus y, and 2 sine y cos x, rather 2 cos x sine y is equal to sine of x plus y minus sine of x minus y. Okay, so this cover all the identities. So look, so if we want to get, how do you use it? So I'll just take one simple example how we use it. So suppose if you want to derive the formula of sine of 15 degree, which is nothing but sine of 45 minus 30 degree. So put the value of sine of a minus b. So that will be sine a cos b minus cos a sine b. Sine of 45 is 1 by root 2. Cos of 30 is root 3 by 2. Cos of 45 1 by root 2, and cos of 45 is 1 by root 2, and sine of 30 is 1 by 2. So that becomes root 3 minus 1 divided by 2. Okay, so we'll go to the last chapter of this trigonometric function series, which is trigonometric equations. Now, what are trigonometric equations? So trigonometric equations are so the equations involving the trigonometric functions as a variable are called trigonometric equations. Okay, so how do you use it? So the way, for example, if we are given sine x is equal to root 3 by 2, so we need to get the value of x. So we know that sine of pi by 3 is equal to root 3 by 2. So this implies that sine of x is equal to sine of pi by 3. Now, sine of pi by 3 also can be written as sine of pi minus pi by 3, which is equal to sine of 2 pi by 3. So is x is equal to pi by 3 or 2 pi by 3. So these are the solutions, and this is the way we use the trigonometric equations. Now there are some theorems here in trigonometric functions. So in trigonometric equations rather. So the theorems are, the first theorem says if if sine x is equal to sine y, then x is equal to n pi minus 1 to the power of n of y, and n belongs to z. So how to prove that? So we are given, so let's try to prove this. So if sin x is equal to sin y, which implies that sin x minus sin y equal to 0. So this here we'll put the formula of sin a minus sin b, which is 2 cos of x plus y divided by 2 and sine of x minus y divided by 2 is equal to 0. So which means either cos of x plus y is equal to 0 or sine of x minus y is equal to 0. So cos 0 is so any odd multiples of pi by 2. So cos x plus y by 2 0 means cos of 2n plus 1 into pi, and sine x minus y divided by 2 is equal to sine of n pi, right? So here we get x is equal to, so we get x plus y by 2 is equal to 2n plus 1 divided by pi, which further gives x is equal to 2n plus 1 pi by 2. So this gives x is equal to 2n plus 1 2n plus 1 plus or minus 2n plus 1 to the power of y. So why we put the minus 1 to n plus 1 to the, because every odd multiples it will be. So when n is equal to 0 becomes minus 1, n is equal to 1, so it will remain minus 1 because y has come to this side, to the right hand side, so minus y. And from here we get x minus y is equal to, we get 2n pi, or x is equal to 2n pi plus minus 1 to the power of 2n into y. So here y becomes plus, so for every 0 to z it should become positive because minus y become plus y. So if we simplify this two, so we combine these two results. So if we combine these two results, what we get, so what we are combining is, so let me write this again. The first one we got 2n plus 1 into pi plus minus 1 2n plus 1 to the power of pi, and the other one we got x is equal to 2n pi to the power of pi, right? So if we combine these two results, so what we get is this, x is equal to n pi, because this is what is common between these two results. So that's the theorem says sin x is equal to sin y, x is equal to n pi minus 1 to the power of n. Similarly, the other theorem is if cos x is equal to cos y, then x is equal to 2n pi plus or minus y. And if tan x is equal to tan y, then x is equal to n pi plus y. So how do you use this? The way it can be used, like for example, if you are given, cos x is equal to half. So cos x is equal to half means this is equal to cos of pi by 3. So x is equal to 2n pi plus or minus pi by 3. So this is because after a, so we just prove just that when cos x is equal to cos y, and cos x is equal to cos y, and cos x is equal to cos y, x is equal to 2n pi plus or minus y. So this is the same thing we used over here. Okay, so this covers the complete chapter of trigonometric functions. So now I will just touch base upon some of the examples here. Uh, just to explain how this whatever we learned till now is being used. So let's see this first example. So what we need to do, find sine of x by 2, cos x by 2 and tan x by 2, where sine x is equal to 1 by 4 and x is in the second quadrant. Okay, so we are given sine x is equal to 1 by 4, x is in second quadrant, which is over here is x. So here we know sine is positive and rest all are negative. So when x is 4, so it means the x range is greater than pi by 2 but less than pi. So this is the range we have. So the x by 2 will be divided by 2 both the sides. So x by 2 is in first quadrant. So x by 2 is in first quadrant. So all are positive. So we have been asked to derive the formula of values of sine x by 2, cos x by 2 and tan x by 2. So everything will be positive because x by 2 is in the first quadrant. So let's start. So sine x is equal to 1 by 4. So very simple, cos square is equal to 1 minus sine square x, which is equal to 1 minus 16. So 15 by 16. So cos x is equal to root 15. Now x is in the second quadrant, so cos x is negative in second quadrant. It will be cos x is equal to minus root 15 by 4. So this is cos x. So now sine of, so we know the formula, cos 2x is equal to 1 minus 2 sine square x. So cos of x is equal to 1 minus 2 sine square x by 2. So sine square x by 2 will be 1 minus cos x divided by 2. So sine of x by 2 will be square root of 1 minus cos x divided by 2. So using this formula here, sine of x by 2, so 1 minus root 15 by 4 divided by 2. So that becomes, so it was minus, so it becomes 1 4 plus root 15 divided by 8. So final simplifications, it becomes 8 plus 2 root 15 divided by 4 square root is sine of x by 2. So in the similar fashions, if we follow these steps, we can get the values. I'm just giving you a hint how to approach. So then you can also solve the values for cos of x by 2 and tan of x by 2. Okay, so the other question is, say for example, we go by this. So we need to prove that sine 3x plus sine 2x minus sine x is equal to 4 sine x cos x by 2 plus cos 3x by 2. So in similar fashion, we'll be using the identities which we have learned till now, and how to use it I will just show you over here. So what do we need to prove? We need to prove sine of 3x plus sine of 2x minus sine of x is equal to 4 sine x cos of x by 2 cos of 3x by 2. So let's take the left hand side. So we have sine 3x plus sine 2x minus sine x. Now let's consider this, which is sine a minus sine b. So if we put the formula of sine a minus sine b, it becomes 2 cos of a plus b divided by 2, which is 3x by 2, and sine of a minus b divided by 2, which is sine of x by 2. Then expand this using the formula of sine of 2 theta. So sine of 2x is equal to 2 sine x cos x. So sine of 3x is equal to 2 sine of 3x by 2 and cos of 3x by 2. So let's put 2 sine of 3x by 2 cos 3x by 2, and then we have 2 cos of 3x by 2 plus sine of x by 2. Okay, now check this out. 2 cos of 3x by 2 common, it becomes sine of 3x by 2 plus sine of x by 2. So this, here again we can put the formula of sine of a plus b, which will be 2 cos of 3x by 2. So it will be 2 sine a plus sine b. The formula is 2 sine of a plus b divided by 2, 2 sine of a plus b, 2 cos, we have a minus b divided by 2, 3x by 2 minus x by 2 divided by 2, right? So this becomes 2 cos of 3x by 2, 3x by 2, 5, x by 2 is 4x by 2, which is 2x, so it becomes 2 sin x, 3x by 2 by x by 2, it becomes x, so it is cos of x by 2. So 2 into 2, 4 sin x cos of x by 2 cos of 3x by 2, which is nothing but this. So So these are the ways, identities are being used for solving questions in trigonometric functions. So I hope you have understood the utilization of trigonometric functions and the different ways of using it in solving complex uh, questions. So if you want to have more sessions being conducted, please reach out to me. This is my email ID, thermobeliever1969@gmail.com, and I can conduct more such online sessions for you folks for other chapters in class 11 mathematics. Please do give your feedback, and I'll appreciate that. Thank you very much and have a nice day.